In this video, we will discuss Roe's method. This is another a very good method to solve the Riemann problem. One thing you should understand that until now, we are only solving the advection equation, and these are the with constant coefficients. So, for example, we solve partial by partial x u bar q is equal to 0, which is the advection equation. And if you talk about the vector form, so we can write it as partial by partial x a, the matrix, or maybe some other quantity, but in this vector form, then we have this equal to 0. So uh, currently, our objective is to solve the advection equation with constant values. But Roe's method and any other method, these are very useful for the nonlinear problem as well. For example, if we have a Inviscid-Burger's equation, which can be written as 1 by 2 u square equal to 0. This is the Inviscid-Burger's equation. Our aim is to find out that method which actually solves the nonlinear scalar equation and nonlinear vector equation. So we start with the advection equation. What happened is we define the fluxes at cell I. For example, we have I minus 1/2, I plus 1/2, and this is cell I. The face value or the flux at I minus 1/2 can be calculated. Fn I minus 1/2 is equal to 1 by 2 A qi minus 1 plus A qi minus P is equal to 1 to m lambda P plus minus lambda P minus WP I minus 1/2. This is the flux that we will use for the Roe's method. This can also be written as, this is, for example, the flux value, maybe over small f qi minus 1 plus f of qi. And these lambda plus and negative means we have a speed, a positive value for the speed and the negative value for speed. And WP I minus 1/2 is the uh, waveform of a wave, and it is at I minus 1/2. Okay, so this was all about the flux. If you want to write, for example, for I plus 1/2, so we can write I, replace I with I plus 1. We get I plus 1/2 is equal to 1 by 2 A qi plus A qi plus 1 minus P is 1 to m lambda P plus lambda P minus and WP I plus 1/2. So that is the I plus 1/2. So the method becomes, when you put these values in the method, the method was qni plus 1, qn plus 1 I qni minus delta t by delta x f I plus 1 half minus fn I minus 1 half. So this was the flux, and we need to put this expression for the Roe's method over here, and we have to put fn I minus 1 half over here. After putting these values, we get the method qn plus 1 I qni minus 1 by 2 delta t by delta x a qn I plus 1 minus qn I minus 1 minus 1 by 2 delta t by delta x. P is 1 to m lambda p mod wp I plus 1 half minus lambda p mod wp I minus 1 half. That what we have for the numerical method for Roe's method. Okay, here one thing we should remember, that here we are using lambda p mod. It means that when we have, for example, in the previous fluxes, here we had plus and minus. These plus and minus can be replaced with mod like this. Lambda plus minus lambda minus. Suppose lambda plus has a speed 3 and lambda minus has a speed minus 4, for example. Even if you put all these values over here, then we have minus 4, 3 plus 4, which is equal to 7. So it means that whatever the speed is, these two lambdas can be replaced with lambda mod, and this lambda mod appears over here. This is lambda mod, this is lambda p mod. Okay. Okay. So that's why there is a mod in this numerical method. So this is the numerical method for Roe's method. Roe's method is a good method, but it has some problems. It has some issues with diffusion and dissipation. Here the lambda plus will be equal to 1 by 2 lambda plus lambda mod, and lambda minus will be equal to 1 by 2 lambda minus lambda mod. That's it. So this is all about the Roe's method. W is the waveform that you can replace this W with alpha and also the eigenvector R. Alpha is shows the strength of the speed of the wave, and R shows the direction of the wave. Thank you for watching.